So let's talk recursion. I'm not going to lie, this talk is pretty advanced. So if you get lost, especially by the end of it, don't feel bad. It took me, it takes many years to really understand functional programming, and there's so much to learn. And all right, let's first of all talk about what our goal is in this talk. First of all, I'm going to explain to you what type algebra is and how to use like isomorphisms and counting to see connections between different types. And then after that, we are going to talk about data types and recursion schemes and how we can recurse over a data structure and transform it into, or rather reinterpret it in many different ways. And we'll see that recursion schemes is actually the same as final tagless. How many of you know what recursion schemes is? Could you just put a hand up? Okay. And how many of you have heard of final tagless? Okay, actually a lot more. It's not surprising. You're doing Scala, right? Recursion schemes is a pain in Scala, but pretty much everybody knows about final tagless. So that's good. And then we are going to talk about free monads. Now, how many of you know about free monads? Excellent. And what about MTL and like final tagless used for effects? Obviously, right? The same crowd. Everybody who knows about final tagless for regular data types knows about it for effects, right? Okay. So first of all, let's talk about isomorphisms. An isomorphism is a pair of functions, two from type A to type B, and from B to A, such that certain laws hold, right? First of all, we need the composition of from and to be an identity function, meaning that if we take an A and apply to it, and then from, we're going to get the same A back, and in the opposite direction as well. Unfortunately, type isomorphisms cannot be expressed like perfectly well in Scala, because Scala doesn't really have dependent types. Now, I would love to write this signature, right? But it doesn't work in Scala because how many of you are familiar with singleton types in Scala, or have used them before? Okay, so the problem is that this doesn't work, right? Because we have an expression, like a singleton expression there, and the compiler just doesn't allow that. So instead, what we do is we just check everything manually, right? We either just look at two functions and say, oh, they form an isomorphism. Or we actually run tests, but we can't really express it without a dependently typed type system. Let's look at an example. So over here we have two types, either of Boolean and unit, or and also a type with three possible values, 1, 2, 3. Right, and we want to show that those two are isomorphic. And it's very easy to do that, right? We can just manually construct an isomorphism. And if you look at it, you can just manually verify that, yes, it is an isomorphism. Like, if you compose those two functions, you're going to get the same value back. Now, how about let's look at a more complicated example. Let's say that we have a function from Boolean to Boolean. Now, can we somehow show that it's isomorphic? First of all, we want to prove that it's actually there are 4 possible functions like that, right? This is not so simple anymore. It's kind of like, well, you have to. Maybe you could somehow enumerate all of those functions, right? How do we do that? Well, one way to do that is to think of functions as tables of values. For every single input, we have one output. And if we just enumerate all possible inputs, we're going to get a large table of output values. So a function can be represented as a tuple, where every single element has type B, and there are A total inputs. So in this particular case, it's a Boolean. So there are two possible inputs, and there are two possible outputs. So we're going to have a tuple of Boolean and Boolean, which has 4 possible values, right? And in fact, using this logic, we can actually construct this isomorphism. When we are going from a function to a type with 4 values, we just call that function on 2 different inputs, and then use those to basically look the appropriate value of type B. Okay, let's look at a more complicated example. Now, here things get a little bit tricky. If you know category theory, you know that nothing is an initial object, and unit is a final object in the category of like Scala. And which means that there is only one arrow, one morphism going to unit, and only one arrow going from nothing to any other object, right? Well, now how can we like actually show it? What if we use our this representation as a tuple? What's going to happen? Well, the first function is going to be a tuple of 2 units, which has only one value. And the second one is going to be a tuple of no elements, each of type int, which again has only one possible value. It's just an empty tuple. Now, if we construct this isomorphism, we are going to discover that there is something strange going on. We actually discard our inputs as if we take an input and then we just discard it. We don't use it, right? It's not very. It might not be that surprising, considering that once we know that every type there has only one value, we already know that value ahead of time. So even if somebody supplies it, it doesn't give us any extra information. But is there like some other way to look at this? Is there some other way to understand what's going on here? We're going to take a surprising detour. And we're going to ask ourselves, well, when are 2 things equal? Because that's how we know, that's how we count, right? If we know that 2 things are different, then, well, we count them as different objects. And if they're the same, we count them as the same object, right? Now, let's look at this 1729. Well, 1729 can be expressed in many different ways. Well, first of all, it's just 1729, but it's also 12 to the 3rd plus 1. Trust me on this. It's also the first number that it can be expressed as a sum of 2 positive cubes in 2 different ways. Now, that 3rd recipe doesn't even tell you what that number is, and you have to like manually find it, and maybe it doesn't exist. Right? So those 3 are completely different ways of thinking about the same number. But are those equal numbers? Well, Leibniz in 17th century discovered this philosophical principle that if you have 2 identical objects, then they have the same properties. And if 2 objects have exactly the same properties, they must be identical. He applied it to philosophy, but it turns out that this principle is very fundamental and applies to programming as well. We can express it logically. we can say that x is identical to y if and only if, for all properties p, p of x is the same as p of y. And the important clarification here is that p ranges over all properties of an object that we care about. And this is going to be, you'll see how this significantly affects what we consider, what kind of things that we consider to be identical and what kind of things we consider to be different. Now, if x and y are expressions, and we can actually observe the structure of those expressions, then they are different, right? Because we can, you take those x and y and you pattern match. And you're going to find that they have different data constructors. But if we forget that structure, if we cannot observe it, then they are exactly the same, right? You cannot distinguish between 1729 and 12 to the third plus 1 at runtime. So ours is too isomorphic. Well, let's look at what kind of properties we can distinguish between them. What kind of properties we can use to distinguish them. Suppose that I ask you to write those two functions, two property functions. How would you write them? The first function takes a Boolean, but always returns a unit. Can you actually see the difference between those two functions that I wrote, right? One pattern matches on an argument, and the other just discards it, right? There is no difference. You cannot really see, like at runtime, you cannot really see any difference. And surprisingly, the same applies to the second function, even though I could write it in many different ways. Like I could return 1, I could return 42. That value, it's going to be in the bytecode, but there is no way to call this function. Like you cannot supply an argument that this function can take, which means that there is no way to look inside of it. There is no way to probe it. Which means that for all intents and purposes, those three functions are exactly the same. They're just different ways of writing the same object. So we cannot see the difference between those two functions as values within our pure functional programming language. However, we can see the difference between them as expression trees. But we don't really care about the latter because that doesn't affect our semantics. Like the code is going to be the same. It's going to work exactly the same. All of the properties are going to be the same. And remember, this only applies as long as we care only about semantics. Let's say we care about performance. Well, in that case, perhaps 2 to the power of 12 cubed plus 1 has slightly different performance characteristics than 42. Than 1729, excuse me. Okay, so those two are isomorphic both from counting perspective and from identity of indiscernibles perspective. Now I say they're isomorphic, it's because they have only one inhabitant, right? And so we can just sort of we can construct a function that maps one value to the other value because there's only one possible value. Fairly simple stuff. Now, there's one more important result, or I guess an interesting result. It said if A and B are isomorphic, then an isomorphism is going to map equal values to equal values and different values to different values. And we can fairly easily prove it by basically just applying, like if we know that A1 is the same as A2, right? We are going to apply 2 to both sides. And then this is going to be B1. This is going to be B2. And so now we know that B1 is the same as B2. And in the opposite direction, you can go using from functions, right? But this, it's like as a homework, think about the following. Is there some equalities? Is there some equivalence relations that are not preserved by function applications, and therefore isomorphisms can actually map equal objects to different objects? And in fact, if you use the standard Scala equality, equals equals, that's going to be the case. And there is only one, there might be a lot of examples, but one in particular is plus 0 is the same as minus 0 as doubles. However, if you apply 1 divided over x to both sides, you're going to get plus infinity and minus infinity, which are not equal according to the default equality. Okay, there are also a few other important isomorphisms, and take a look at them and see if you can, just see how you would write, how you would construct them. Hopefully, it's pretty clear that all of this are just pattern matching. The only tricky one is distributivity, like where you go from tuple of A and either BC to either a tuple of AB or a tuple of AC. But it's fairly simple as well. Now, what if we replaced either with a plus, tuples with a multiplication, nothing with 0, and unit with 1? Does it look familiar to you? Please show, like a hand, if you think that this is like very familiar. Right? What is this? What does it look like? Arithmetic. Yes, just regular arithmetic, right? Like if you take natural numbers, you're going to get exactly the same laws. It's very interesting how it just works out. There is like a mapping between two different, completely different, algebras, I guess, between types and then natural numbers. Now, there are a couple more important results that we'll need. First of all, functions can be curried and uncurried, and that's an isomorphism. And there's this first result. It's actually called, sometimes called pairing. Like you can pair two functions together, or you can unpair them. And the idea is that, well, if you have a function that takes either one of two arguments, then you can represent it as two functions, each taking only one half of the argument. So if you have a function that takes either a, b, and returns a c, you can decompose it into two functions. One takes a and another takes b. Basically, those are going to be your two cases in a pattern match. And it turns out that this is fairly obvious as soon as we replace function application with exponentiation, or I should say, it's not obvious at all, but rather there is a correspondence between natural numbers and functions, between natural numbers and types. So if we rewrite it, and notice that the order changes, but other than that, it's basically just straightforward mapping. If we rewrite it using exponentiation, then suddenly it's very, very clear that, yeah, those two things are equal. Okay, so we're not going to go through too much of type algebra anymore, but just to sum it up, the way to think about, one way to think about things is, either is a plus, tuple is multiplication, unit is 1, nothing is 0, and so on. Like Boolean has 2 possible values, so sometimes I might write it as 2, and that's just an easier way to think about things. Okay, and one more theorem. If A is isomorphic to B, then f of A is isomorphic to f of B for any functor. That includes phantom, covariant, contravariant functors, whatever. And it's fairly simple to prove using functor laws. We basically take in order to map f of A to f of B, we just use our function 2, and we map using it. Right, I'm using sort of a Haskell syntax here. So we map using 2, and in order to go in the opposite direction, we map using from. And then to prove that it's actually an isomorphism, we can use functor laws. Map to composed with, map from is just mapped to composed with from. That's one of the functor laws. And then we simplify this expression as identity, which is an isomorphism law. And finally, we use functor laws again and end up with an identity, which means that it's a proper isomorphism. And one more thing, I'm going to be using this symbol bottom for instead of nothing, because nothing is a little bit too verbose for me. It just doesn't fit into slides. All right, now let's talk recursion. So let's say we have a list, and we would like to fold over it. Now, that's just a standard fold right. As you can see, I'm pattern matching. If I see a nil, I just return my seed value. And if I see a const data constructor, then I'm going to first fold the rest of the list, and then I'm going to combine the two values. Everybody's familiar with fold right, right? Good. Now, why do we want to fold? Well, it turns out that fold is actually a fairly, like if you have a fold over a data structure, then you can express every single function using just fold. And it's a very non-trivial fact. Like you would think that, well, like zip is probably not possible to implement using fold R, but consider that a homework assignment, it is possible. It is possible to implement using fold R. You just first fold over the first list, you return a function that takes another list, and it folds over that. Let's look at a slightly more realistic example. Let's say we have expression trees, addition, multiplication, and literal values. We can similarly write a fold R function of sorts. It has the same structure, but maybe if you haven't seen it before, just take a look for a few seconds, and you should be able to see that it kind of like does the same kind of thing as fold right. If it sees any of the leaves, like literal values, and it just applies a function to them. And if it sees recursive structures, and it first folds the two components and then combines them together. And the same idea applies, right? We can reinterpret expressions to many different forms using this fold right. R, fold R. So for example, we can evaluate them. We just pass in, like if we see a literal value, we just return it. If we see addition, we add two things together, and if we see multiplication, we multiply them together. And we can convert them into like strings. Pretty much, as I said, if you have fold R, if you have a function of this shape, of this like with this kind of that looks like that, then you're going to be able to write everything in terms of just that function. Now let's take a look at the type of fold R. You can see that it takes three function arguments, right? Let's first combine our arguments together. Remember that pairing theorem that we talked about? Like if you have something that takes multiple, like either one of two arguments, you can split that into two separate functions. And in the other direction, you can combine two functions that take, you have one function that takes an A, another function takes a B. You can combine them into one function that takes either one of those values. There are two important concepts in here. First of all, there's algebra, the blue thing. Oh, the red thing. And also pattern or signature functor. So let's first talk about algebras. In mathematics, and more specifically in abstract algebra, an algebra is like a collection of, it's a set, but also a collection of operations on that set. And usually, you add like maybe some laws, and also you say that the operations are closed. Like you cannot escape the set by just using the operations of an algebra. In category theory, an algebra is, or rather an F algebra. It's sort of like, in category theory, it's just a generalization of the same idea. And we'll see exactly how it looks like on this slide. Okay, so in category theory, we have some functor F and some carrier object C. And the function from FC to C is called an algebra. Now, it looks fairly complicated, but it expresses a very simple concept. F of C is some way of combining things of type C together. And the mapping FC to C reduces that to whatever is contained inside of that structure. So let's look at our example and define a signature functor. So in our case, X per F there is like all the ways you can combine values together within this algebra. So we can either add two values together, or we can multiply them, or we have literal values. Those are all possible ways of combining things together. But this is not an algebra. This is just a signature functor, right? It defines a signature, like all possible operations that we can do. And then an algebra over here says that, well, if we know how to take something that combines like an operation over Z, we can reduce it down to the value of type Z, right? And this way of expressing fold R, or our original function, is actually called recursion schemes. And so you can see, like over here, what's happening is that if we see a literal value, we're gonna just directly give it to our algebra. But if we see, let's say, addition, right, we're gonna fold both sides of an addition, pack them up inside of this addition operations, and pass them to our algebra. And the algebra is going to reduce that down to just a single value of type Z. Okay, now let's talk recursion schemes, right? What is recursion schemes? Well, the idea is that if you have a recursive data structure, then you can, instead of using that recursive data structure, you can think of like the signature functor, which has holes in it. Whenever you have a recursive, wherever you use a recursive value, it has a hole in it. Right, so over here we have addition, but a signature functor here would have like sort of like instead of having a recursive recursively referring to itself, right? It just has a hole here. And the way to think about it is that X per F is just a single layer of our recursive data structure. If you take some expression and you just look at the very, very top level of it, right, you can see that, maybe the top operation is multiplication. It multiplies two sub-expressions together. And just that one operation is your signature functor. And then once we have this concept of signature functors representing just one layer of our recursive data structure, we can say, well, for any kind of expression, I should be able to extract that one layer out. And in the opposite direction, I should be able to embed one layer containing subtrees. Just take like a layer containing subtrees of and the operation, and just create a tree out of it, a recursive data structure. Does it make sense? So far, so good? Now we can use this to rewrite our fold RS as a much simpler expression. However, it's simpler in terms of the line count, but it might appear to be a little bit more, actually a little bit more complicated, right? But what we are doing here is that, first of all, we are projecting, meaning that we're extracting a single layer of our data structure. Then for every subtree within that single layer, using map, we are going to fold that subtree. And then finally, we're going to apply our algebra to reduce this one single operation down to a single value of type Z. And we can further generalize this idea. We can use a type class, and that's basically what recursion schemes are. We can use a type class with a function to project, maybe a function to embed, a single layer, and so on. How many of you know Matryoshka? It's a Scala library. Okay, good. So that library actually has all of those type classes, and if you're interested in this topic, you should check it out. It doesn't really have like a lot of documentation. Unfortunately, there's just like not a lot of information about recursion schemes online that is like easy to understand for beginners. Okay. Now, what's interesting is that we haven't lost any power by, going to this different representation of our fold function. Using our fold rs function, we can similarly express, evaluation, or we can convert our expression to strings. And that's because what we were doing, we were just transforming one way of one type into an isomorphic type, right? So we haven't really lost any of the power. We are sort of like going between different representations of the same idea. Now let's go back to our types again. Now, what if, instead of extracting a pattern functor, we were to extract our algebra? Right before, we defined a type for this part. It was x per f. What if we take this whole thing and define a new type for it? Now I cheated a little bit here because, as you can see, I went back. Instead of using this representation, I went back one step and I used this one. And that's because it's just a little bit easier to represent in Scala. Like a tuple of stray functions is basically just a record or a trait. Does that look familiar to you? So everyone who knows like final tagless should be able to immediately say, oh, that's just like my final tagless algebra, right? And notice the word algebra once again. And we can rewrite our fold now, this time using this final tagless approach, using final tagless algebra. And it's fairly straightforward. You fold, if you see an addition, you just fold both sides, and then you pass them to the algebra. And it turns out that we can use our function again, to do whatever we want with our expressions, to reinterpret them in different ways, right? Just like before, we have the same exact power. We haven't lost anything. We just went between different representations of the same idea. And this is usually called final tagless, right? But in final tagless, we normally pass things implicitly, right? You don't have to. And in fact, I think that most Scala programmers do not pass things implicitly. But if you're using Haskell and you have access to like easy new types, that's a more natural approach. And indeed, what if we rewrite our algebra as a type class and pass it implicitly? We get yet another way to express our function fold. This time called fold ft, which instead of taking x per a explicitly as an argument, it just resolves it implicitly. And once again, unsurprisingly, we can implement all of the same functionality using this approach. So let's take a look at all of those functions that we've just derived, side by side. So simply by transforming an expression using isomorphisms, using just transformations of the structure, we were able to arrive at recursion schemes, final tagless, and like different versions of final tagless, and just regular fold. So really, all of those things are exactly the same idea. It's just like different It's kind of like people just talk about them separately, but really they are the same exact idea. And you should think of them as the same idea. You're just abstracting over recursion. You're just trying to figure out, like, how can I rewrite my recursive functions in like different ways? How can I fold over recursive structure in different ways? Now, I told you that every single function that you can write on lists can be expressed in terms of fold R. That's a very interesting fact, because it turns out that it has like very deep roots, and it's connected to different representations of data types. In particular, expressing a recursive data structure in terms of its fold R, or sometimes it's called catamorphism as well, is called, and I'm not entirely sure how to pronounce the name, so Boehm-Berardici, I guess. So it's just a different encoding of data types. Now, we had, like, if you look at the signature of fold, it looks like this. But the problem is, this is not an isomorphism, because this quantifier is, it's just a little bit, it's kind of like, we cannot easily, like, this is not an isomorphism. It's just like fold R itself is not doesn't have the right like shape, because we just have a function here going from expr to all of those different representations, right? But if we move the quantifier, if we say that we can go from expr, essentially we are just partially applying a function, right? We have a function on expressions. And instead of taking first our type parameter and then an argument of type expr, right, as this, we're going to reverse that. And so we are first taking our expr, and then we are taking a type parameter and the rest of the functions, right? And we can do that. We can just move that quantifier. And it turns out that this is an isomorphism. And this part is called Boehm-Berardici encoding. And in fact, we can construct that isomorphism explicitly. So over here we have our algebra. And I'm going to encode my values of type Z using Boehm-Berardici encoding. So instead of having a value of type Z, I just give you a way to fold over it. And it turns out that that is enough to reconstruct the original value, right? Because all we need to do is to fold over it, and every single time we see a literal, we just construct a literal expression. Every time we see addition, we just construct an addition. And every time we see multiplication, we construct a multiplication. And in the opposite direction, it's just fold. That's it. And so in mathematics, so we talked a little bit about algebras. Well, it turns out that algebras themselves form a category, and there is an initial algebra, or actually a lot of initial objects, but all of them are isomorphic. And any one of those has a carrier that is like the most informative representation of a type, meaning that it's like has the most information possible. And that object is called as a carrier of an initial algebra. And so in our case, expr is actually the carrier of that initial algebra. Now, we're not going to go into too much detail here, but the important takeaway is that every recursive type is isomorphic to this different representation, right? It's isomorphic to its fold R. Now that's interesting because we can think about it slightly differently. Every object is isomorphic to the set of things that we can observe about it. Now, if you know Yonah dilemma, you might have some very interesting ideas right now, and I would love to talk to you about that. And the reason we can do that is because, well, this is kind of like an intuitive picture. If we take any object and we map to all of its properties, like all of the things that we can observe about that object, then that is actually going to be an isomorphism. We are sort of taking everything that we know about an object, right, and we are packaging it up. Well, that is essentially what the object was originally, right? Like now we can, in our code, we can replace every occurrence of that object with this tuple of all properties, and we won't be able to distinguish between the two. So, it's sort of like, mostly intuitively, you can understand that, well, we cannot distinguish between, since all property, if two objects are the same, right, they are going to have all of the same properties, therefore they are going to be represented by the same tuples of properties, and in the opposite direction, the same logic applies, right? If two tuples are the same, then two objects have the same properties, and therefore they are identical. And that means that this mapping is an isomorphism. Okay, now let's talk free monads. Now, free monads is a pretty difficult topic, but to give you some intuition, basically, free monads allow us to express how many of you are familiar with monads in general? Could you raise a hand? Okay, excellent, right? Pretty much everybody. So the idea is that free allows it to capture either a pure value or a computation suspended inside of f. So consider the case where f is I/O. Pretty much nobody should, normally people would not do that, but imagine that, right? Then you either have a pure value of type A, or you have like more steps suspended inside of I/O. So that's the suspend constructor here. And free monads can be reinterpreted into any other monad as long as we supply a natural transformation from F to G. What that means is that for, I give you any kind of effect F, and you should be able to transform it into an effect in G. Now, the reason they are useful is because, and this is kind of like a common idea in this talk, right? We can reinterpret things. We write them once and we reinterpret them in many different ways, right? And free monads allow us to do exactly that. We write one expression and then we can run it in different target monads. So, imagine that you have this kind of API. Now, obviously this is side effectful, but this is just for illustration purposes. So we have a get function that takes a key and returns an int, and we have a set function. So it's sort of like a storage with 2 to the power of 32 elements, and each of them is an int. Now, using free, we can write a program that uses this API. And I just wrote some simple programs that takes the first element, sets the first element to the old value plus 1, and sets the second element to the old value of the first element plus 2, and then returns an x. Now we can reinterpret that in different ways. We can either interpret it using side effects. Maybe you have like some sort of Redis storage or some sort of database that you query. Or we can interpret that using state monad, which means that interprets that purely. So we can test our code without running it against an actual database. Now, to do that, in order to actually use free, you have to define your pattern functor once again that represents different possible operations that you can do. And you can, if you look at this thing here, this service F, it has a weird shape because you see our original function get would take a key and return a value of type int. But here in order to make it a functor, we actually, it's sort of like a functor has to contain, it has to contain some values that we can map. And one way to think about this is that in order to suspend a value inside of this effect, in order to suspend like free is essentially a sequence of actions. And this represents a single layer of that sequence. And what free does is that it needs some, just like a list, we can think of tail of a list as a whole where we could, we put the rest of the list, right? And the same here, the same idea applies here. This A is like the rest of our computation. So we're going to run get using this key, and then we're going to pass the result to the rest of our computation, and we're going to, sort of like get at the tail of this list, if you think, by an analogy here. And our two operations here, get and set, they essentially just use suspend constructor free in order to suspend a single effect. So for example, get. And then as soon as they get a value back, they're just going to use pure to just return it back, right? I mean, it's complicated stuff, and this doesn't really matter to us that much. And then, like once we have that definition, we can actually write an interpreter. And here I have like a very simple interpreter and also like partial interpreter technically over state. Now, okay, now in Scala and actually, in Haskell as well, people normally use a different representation of free. And basically, before we had this problem where in order to have a sequence of actions, we had to have a hole in our type so that we could store the rest of the sequence, right? But you can use this different representation, which allows you to essentially, instead of having like a list kind of structure, you actually have an additional constructor that allows you to concatenate one computation together with its tail. It's a little bit cleaner to use, but it's not substantially different. It's the same idea. And like we can also define our operations and an interpreter for those operations. Now, remember this idea that every type is isomorphic to the set of things we can observe about it. Now, the only thing we can observe about a free monad, the only thing we can do with a free monad value is we can fold over it. Obviously, if you have a particular implementation in cats or somewhere, you might be able to observe more things about it. You might be able to pattern match, but really you shouldn't, because that is not part of what defines a free monad. Free monad is specifically something that represents the computations that can be folded using any monad. So the only things that we can observe about value of type free FA are the results of running it in some monad. Those are the only things that we should observe of a mathematical object that is called free monad, right? Okay, well, let's apply that. Let's apply our principles that everything is isomorphic to the set of its properties or observations that we can make about it. We can rewrite our free as just run free, as a function that takes a natural transformation and returns you a new computation in the monad G. That's like the way to fold a free monad. And what's interesting is that if you do that, you can rewrite all of your code using this new encoding, and nothing is going to change. Like, the API can remain the same. You have all the same instances and so on, right? So, in fact, it turns out that, yes, they are isomorphic. Like, this is exactly what a free monad is. Now, let's look at this type. And let's rewrite this particular term, the underlined term, as a constraint on G rather than as a natural transformation. We are going to define some type A of G, right? Such that, by definition, is going to be A of G is this natural transformation from F to G. Now, what is A? Now, let's look at a concrete example. So we have service F of A, right? And then our A of G is just a natural transformation, right, from service F to G. You might lose me here, but basically, the first step, in order to transform this expression, the first step is going to be to express it as a GADT, express service F of A as a, it is a GADT, but we want to express it as an ADT. Now, GADTs are basically ADTs that also take type constraints as arguments. Normally, those type constraints are, passed implicitly by the compiler. They actually are never materialized. They just, during the type checking, the compiler checks that things are actually equal. But one way to think about this is that, well, get, it fixes. We can think of get as a value of type service F of A, where A is fixed to be an int. Or, I guess another way to look at this is, remember that other representation of pattern functors that we had that contain functions in it? It's kind of like fixing all of those functions to be identity. So if we use this representation, right, or you can think of it as the following, like this natural transformations that we have, right? If you pattern match and you see get, then you are going to know that x is int, right? imagine that inside of here, inside of run, I pattern matched on my value, right? And I saw that the value, right, was get of some key. Then I would immediately know that x is also an int. And that's where this term comes from. So I would get a proves that x is an int, but I would also get, like the key itself. Similarly, if I pattern matched and I saw set, then I would get two ints, key and value, and I would get a proof that x is a unit. Now let's transform this expression. First, we are going to technically unpair it, not uncurry. So instead of having a function that takes either one of those two arguments, we're going to have two functions that take both sides of an either there. Then we're going to distribute the universal quantification. Basically, if we have two functions, if we have a tuple such that we can produce both components for any type x, then we can produce each component for any type x as well. Now, if we have for all x, a function that takes any type x, but also it proves that x is int, it's basically a function that takes an int, right? Because the only things that you can actually pass in is an int, because you also have to pass a proof in. Right, so that allows us to remove this universal quantification, and we just end up with a function going from int to g of int. And the second subtype is transformed into a function that takes two ints, and x is fixed to unit, so it returns a g of unit. And if we use this type, like if you use this type, then you'll see that what you end up is just colloquially known as an algebra. So let's rewrite our free monad accordingly. This time we're going to, instead of passing f, type constructor f, we're going to pass an algebra that restricts the values of type g. It restricts restricts the type of g. Right? Does that look familiar to you? Right? It's final tagless encoding. And notice that if we have this free A of service algebra and end, we can just rewrite it. We can just remove that free A, right? Because really, we don't need it. It's just a single function. So let's just use that single function instead of wrapping it inside of an object. And we get exactly what we usually use. We usually call final tagless. So we just went from free to final tagless. Now we could also make our algebra a type class and pass it implicitly. And so, what is the takeaway? Like, what do I want you to sort of remember from this talk? Well, first of all, free is the same as final tagless. It's not that they're going to perform the same. It's not that they're, you're going to write, the code is going to be the same. It's not that the amount of boilerplate is the same, right? It's that conceptually on the level of they have the same, they represent the same idea. And both give us an ability to write our programs in a domain-specific language and then have it reinterpreted in different ways. And that there's also an isomorphism between the two. Like you can go from one representation to the other in both directions, and you're not losing any information by doing that. You're not losing any power by doing that. All right, let's just sum everything up. We first talked about identity of indiscernibles. And I personally really like the principle because it allows me to think about things. It's kind of like a very powerful tool of thinking about identities and thinking about like properties of your programs and of anything really. And then we also talked about how identity of indiscernibles is connected to isomorphism, and we also touched a little bit on counting, like counting type inhabitants. And then we talked about type algebra, how types are actually correspond to natural numbers, how you can sort of like go in between two different ideas, how they're connected together. And we also talked about, folds being the same as recursion schemes, being the same as final tagless, right? Then we talked about isomorphisms as we talked about Bohm-Berardinci encoding and the fact that every type is isomorphic to, so like, you could say initial algebra. Or you could say that every initial algebra carrier is in some sense isomorphic to every other initial algebra carrier. And then also about, we talked about objects being isomorphic to the sets, to tuples of all of their properties, right? Also a very powerful idea, a very powerful thinking idea. Very powerful reasoning idea. And finally, I showed you that free is basically the same as final tagless. So I would say that the takeaway here is really that things are connected in multiple different ways. And I find, in even isomorphisms themselves are ways to connect things together, right? We take two types, and if they are isomorphic, in some sense they are equivalent. And that equivalence actually corresponds to the equality of the number of inhabitants of those types. So you sort of like can see all of these things connected by a mesh of different like equivalences and equalities. All right, that's the end of my talk. I hope I hope that you will, remember this idea that everything is connected. And I would say that this is what's wonderful about function programming, is that you learn about things and you discover those connections and you realize that you sort of like can pack things more densely in your mind. Like all of your ideas, over time, you're gonna come up with better representations of all of those ideas. Well, thank you for listening. And if you have any questions, I'm ready to take them. Easy then. Well, that's good. Well, I can add that if you're interested in this counting topic, I also have a blog article on specifically that topic. So you can basically just go to my website and it's over there. Yep.
Right. So I have a question about the isomorphism between the church encoding and the actual data type. So you've demonstrated the isomorphism, you implemented it, so that's fine. I just have a bit of a contradiction in my head because in theoretical computer science, you talk about primitive recursive functions, right?
Right.
And primitive recursive functions are exactly the functions that you can express with a fold. So let's say you have the natural numbers. There are a lot of functions that you can implement on these natural numbers using fold. But in theoretical computer science, you also learn that there are functions that you can compute, but that are not primitive recursive. So I don't really know how to reconcile these two things. Maybe you have an idea there. Maybe there's just a misunderstanding there.
That's a very interesting question, and I have no idea. Yeah, I would need to think about it.
Okay, because I don't. When I saw you talk, it all made sense. But yeah, there's probably just a misunderstanding there somewhere. Let me know if you figure it out.
Okay,
really interested.
Yes, we should talk about this after the end of this talk.
続いて他の質問がある方はどうぞ。
Well, I guess we can just end this talk. Once again, thank you everyone for listening. Hope you enjoyed it. If you are interested in learning more about this stuff, you can read, some of my blog articles. They're not very well written. Sort of like, I write down the stuff that I think about, and so I write it mostly for myself than the others. But I think that this is like very powerful. There are very powerful thinking tools about your code, and it's just learning functional programming makes you really appreciate the work you're doing. Like if you discover that you are actually doing something interesting and not just writing a bunch of stuff that you don't just code. You sort of like see all of those connections, and that's what makes me excited about functional programming. And I hope that as you learn more, you're going to get really excited about that as well. Okay, thank you, and thanks for listening. Yeah.
拍手お願いします。